there is one planet in our solar system that turns a mission into a one-way trip. Not because your ship would explode instantly, not because you would hit a solid surface and shatter, but because once you fall into its gravity, the numbers stop working in your favor. Jupiter is so massive that escape becomes a calculation you can't win. Its radiation can fry electronics before you even see the clouds up close. And if you descend too far, the atmosphere becomes an ocean with no bottom. No landing, no rescue, no return trajectory. Go to Jupiter and Earth becomes unreachable. Welcome to Simulation Hypothesis. This is where we question the grand promises of space and examine what the physics actually allows. No hype, no fantasy, just the reality hidden behind the beauty. If you're new here, subscribe and stay with us, because sometimes the worlds we admire from a distance are the ones that quietly remove every path home. Many people call Jupiter the protector of Earth, the gravitational guardian, the massive shield that captures comets before they reach the inner solar system, the big brother of the planetary family. And to some extent, that's true. In 1994, when Comet Shoemaker, Levy 9 broke apart and slammed into Jupiter, astronomers watched fragments the size of cities explode in its atmosphere. The energy released dwarfed humanity's entire nuclear arsenal. Dark scars larger than Earth spread across the planet's cloud tops. Jupiter absorbed the impact. It protects us by swallowing threats. But here's what rarely gets mentioned. Jupiter doesn't protect anything out of kindness. It captures, it absorbs, it dominates. And if you go there, truly go there, you are no longer under its protection. You are inside its territory. And Jupiter is not dangerous in the dramatic way people imagine. It doesn't kill you instantly. It does something worse. It removes your ability to leave. Jupiter contains more mass than all the other planets in the solar system combined, more than twice as much, in fact. Its mass is 1.9 times 1027 kilograms. That number defines everything. Because gravity is not about how something looks, it's about how much mass it contains. And Jupiter's gravitational well is second only to the Sun's. At the altitude of its visible cloud tops, the level scientists define as 1 bar pressure, equivalent to Earth's sea level. The escape velocity is approximately 59.5 kilometers per second. Earth's escape velocity is 11.2 kilometers per second. Jupiter requires more than 5 times that. And that is before you descend even a single kilometer. Let's make this practical. To escape Earth, NASA built the Saturn V rocket, a 110-meter tall launch vehicle that burned nearly 3,000 tons of propellant to push astronauts toward the moon. That rocket delivered about 11 kilometers per second. Jupiter demands nearly 60, and you don't get to launch from solid ground. Before we even talk about descending into Jupiter, consider orbit. NASA's Galileo spacecraft arrived at Jupiter in 1995 after a 6-year journey using multiple gravity assists. The Juno spacecraft, launched in 2011, took 5 years and required a deep space maneuver near Earth to gain enough energy to reach Jupiter. Arriving at Jupiter means falling into its gravity well at enormous speed. To avoid slingshotting past the planet, Juno had to perform a 35-minute engine burn to slow down enough to be captured into orbit. That burn was not optional. Without it, Jupiter would not have allowed orbit. Now reverse the situation. To leave Jupiter from low orbit, you must supply nearly the same energy in the opposite direction. Even accounting for orbital velocity, you are still facing a delta-V requirement that chemical rockets simply cannot provide without absurd mass ratios. And every kilogram of propellant required for departure must be launched from Earth first. The rocket equation compounds before you even leave home. This is where the trap begins. Now add radiation. Jupiter's magnetic field is the strongest of any planet in the solar system. Generated by electrical currents in its deep metallic hydrogen interior, the field is about 20,000 times stronger than Earth's. It traps charged particles, electrons and ions, and accelerates them to extreme energies. The result is a radiation environment so intense that spacecraft electronics degrade rapidly. According to data from the Galileo mission, radiation levels in parts of Jupiter's magnetosphere can reach tens of millions of rads. For comparison, a dose of about 5 sieverts can be lethal to humans without treatment. Jupiter can deliver that in short exposure times near its inner radiation belts. NASA designed Juno with a titanium radiation vault nearly 1 centimeter thick to shield its most sensitive systems. Even then, mission planners minimized exposure by placing Juno in a highly elongated polar orbit. It dives in. It gets out. It never lingers. Because lingering means degradation. If you descend into Jupiter's atmosphere, you are not minimizing exposure. You are moving toward the core of the system, generating that radiation. Your electronics degrade. Your shielding accumulates damage. Your margin shrinks. But radiation still isn't what traps you. Gravity does. Jupiter's upper atmosphere is composed mainly of hydrogen and helium, with ammonia ice clouds forming the visible bands. At the cloud tops, temperatures are around -145 degrees Celsius. Cold but manageable with insulation. Descend deeper and pressure increases rapidly. Within 100 kilometers, pressure multiplies several times. Within a few hundred kilometers, temperatures begin climbing sharply. By the time you reach pressures of 10 to 20 bars, temperatures exceed the boiling point of water. In 1995, NASA's Galileo atmospheric probe descended into Jupiter and transmitted data for 57 minutes before it was crushed and destroyed. It reached pressures around 22 bars before contact was lost. That probe was never meant to return. It had no engines powerful enough to fight 2.5 times Earth's gravity inside a deepening atmosphere. And here's the critical detail. You do not need to reach crushing pressures to lose your return path. You only need to descend far enough that the delta V required to climb back out exceeds the propellant you have left. The rocket equation is unforgiving. The velocity change a spacecraft can achieve depends on exhaust velocity and the natural logarithm of its mass ratio. To gain more delta V, you must exponentially increase propellant mass. But propellant adds weight. Weight increases the force gravity exerts on you. Gravity demands more thrust. More thrust consumes more propellant. The loop feeds itself. On Earth, engineers work at the edge of this equation. That's why rockets are mostly fuel. That's why we stage them, discarding empty tanks to shed mass. On Jupiter, staging inside an atmosphere is not realistic. There is no platform, no recovery, no second chance. An atmospheric drag compounds the problem. Drag increases with the square of velocity and directly with atmospheric density. The faster you try to accelerate upward, the more the atmosphere resists. Your engines burn harder. Heat builds. Fuel drains faster than planned. And every kilometer you descend increases the gravitational potential energy you must repay to escape. There is no discount. If you fall 200 kilometers deeper than intended, you must supply the energy required to climb that 200 kilometers again, plus enough to reach orbit, plus enough to reach escape velocity. And Jupiter's gravity is not subtle. At the cloud tops, gravitational acceleration is about 24.8 meters per second squared, roughly 2.5 times Earth's gravity. Every kilogram weighs more. Every structural beam bears more load. Every engine must work harder just to hover. Now imagine this. You descend to sample atmospheric data. Instruments measure ammonia concentration, wind shear, lightning activity. You remain cautious. You ignite engines to ascend. At first it works, but drag is higher than expected. Turbulence from Jupiter's jet streams destabilizes orientation. Fuel consumption increases beyond margin. Halfway through ascent, calculations update. Remaining propellant cannot generate the required velocity to reach escape trajectory. You are still intact, still transmitting, But mathematically, Earth is gone. You may rise temporarily, but without sufficient velocity to escape Jupiter's gravitational well, gravity will reclaim you. And once fuel is exhausted, you descend again, deeper than before. That is how Jupiter eats you. Slowly, not with fire, not with impact, with numbers. And once those numbers cross a threshold, there is no return trajectory left to calculate. The moment you lose escape velocity, Jupiter stops being a destination. It becomes a descent. And the deeper you fall, the more the planet changes around you. Above you, the clouds continue their rotation, bands of ammonia ice sliding past each other at hundreds of kilometers per hour. But below you, the atmosphere thickens in a way that has no parallel on Earth. Jupiter is not a gas giant in the way a cloud is gas. It is a compression machine. At increasing depth, hydrogen, the lightest element in the universe, is forced into states that do not exist naturally anywhere on Earth's surface. Pressure builds smoothly. 10 atmospheres, 20, 50, 100. The Galileo probe survived until around 22 atmospheres before structural failure. But that was only the beginning of Jupiter's depth. Beneath that lies thousands of kilometers of increasing pressure. By the time you reach pressures of several hundred atmospheres, temperatures climb into the hundreds of degrees Celsius. Continue downward, and you enter thousands of degrees. At around 1 to 3 million atmospheres of pressure, hydrogen transitions into a phase called metallic hydrogen. This is not metaphorical. Laboratory experiments on Earth have attempted to recreate this state using diamond anvil cells and shock compression. Under immense pressure, hydrogen's molecular bonds collapse and electrons move freely, allowing it to conduct electricity like a metal. Scientists believe this vast ocean of metallic hydrogen inside Jupiter is what generates its magnetic field through dynamo action. And that magnetic field is not passive. It extends millions of kilometers into space, shaping plasma, accelerating charged particles, and maintaining radiation belts that would cripple most spacecraft within hours or days if unshielded. But you never reach metallic hydrogen intact. Long before that depth, structural failure ends the mission. The pressure gradient alone ensures it. Unlike Earth, where atmospheric pressure increases modestly with depth until you hit solid ground, Jupiter provides no solid boundary to push against. Pressure rises continuously because there is no surface to absorb force. You are suspended in an ever-thickening medium, and gravity never relaxes. Jupiter's internal structure does create some variation in gravitational acceleration with depth, but that does not save you. You are still deep inside a gravitational well that demands nearly 60 kilometers per second to escape. And that requirement does not shrink simply because you are inside it. Now consider propulsion. Suppose, in some future scenario, you arrived at Jupiter equipped not with chemical rockets, but with advanced nuclear thermal engines, perhaps even fusion propulsion. Nuclear thermal rockets offer higher exhaust velocity than chemical systems. That means more delta V for the same mass ratio. But they do not negate gravity. To climb out of Jupiter's gravity well from within its atmosphere would require not only high exhaust velocity, but sustained thrust sufficient to counter 2.5 times Earth's gravity, while fighting drag from increasingly dense hydrogen. Ion engines are efficient but produce extremely low thrust. They are useless in dense atmosphere. They work in vacuum over months, not seconds against heavy gravity. Fusion propulsion remains theoretical at meaningful scales. Antimatter propulsion remains impractical and extraordinarily dangerous. Even the most optimistic propulsion concepts must obey conservation of energy. The energy required to escape Jupiter is not negotiable. And here is where the trap tightens further. Jupiter emits more energy than it receives from the Sun. This has been measured. The planet radiates roughly 1.6 times the energy it absorbs from sunlight. That excess heat comes from residual gravitational contraction, the slow compression of the planet under its own mass, a process known as Kelvin, Helmholtz contraction. That internal heat drives convection. Convection drives storms. Storms drive vertical mixing. You are not descending into calm layers. You are entering a dynamic system powered from within. The Great Red Spot, that massive storm larger than Earth, has been raging for at least 350 years. Wind speeds around it exceed 400 kilometers per hour. Deeper jet streams may move even faster. Lightning has been detected in Jupiter's atmosphere, powerful electrical discharges inside deep water clouds. The Juno spacecraft has recorded radio emissions associated with Jovian lightning. These are not surface storms. They are deep atmospheric phenomena embedded in thousands of kilometers of fluid motion. If you descend, you are not falling straight down. You are carried sideways, dragged into shear zones, pulled into vertical currents. Your orientation shifts. Your ascent path becomes unstable. And every correction costs fuel. Fuel you no longer have in surplus. Now consider rescue. Let's assume a catastrophic systems failure during descent, but the vehicle remains intact for some time. Earth is between 628 million and 930 million kilometers away, depending on orbital alignment. Radio signals travel at the speed of light. That means between roughly 35 and 50 minutes for a round trip. If something goes wrong, Earth knows nearly an hour later. If Earth launches a rescue mission immediately, ignoring planning time, the fastest transit to Jupiter with current propulsion technology takes years. Galileo took 6 years. Juno took 5. Even with optimized transfer windows and gravity assists, you are looking at multiple years of travel. No crew can survive uncontrolled descent in Jupiter's atmosphere for years waiting for help. And even if a rescue craft arrived in orbit, how would it retrieve you? There is no surface rendezvous point, no stable landing zone, only a descending trajectory into increasing pressure. Jupiter eliminates rescue not with violence, but with scale. Now let's return to orbit for a moment. Suppose you never descend. Suppose you remain in orbit around Jupiter. Even there, survival is a ticking clock. Radiation accumulates. According to NASA mission data, unshielded electronics near Jupiter can fail rapidly. Juno's radiation vault was specifically engineered because scientists knew exposure would degrade instruments over time. For humans, long-term exposure would be catastrophic without heavy shielding, and shielding adds mass. Mass increases propulsion requirements. Propulsion requires fuel. Fuel increases mass again. The equation circles back. Even maintaining stable orbit requires periodic burns to adjust trajectory and compensate for gravitational perturbations from Jupiter's massive moons, Io, Europa, Ganymede, and Callisto. Io, in particular, orbits within intense radiation belts and contributes plasma to Jupiter's magnetosphere through its volcanic activity. You are not alone in orbit. You are inside a dynamic gravitational system with multiple massive bodies interacting. Every maneuver costs fuel. Every day and radiation degrades systems. And departure still requires enormous delta V. Now consider psychology. On Mars, if something fails, you can stand on ground. You can attempt repairs. You can ration supplies. You have time. On Jupiter, there is no ground, no horizon. If you descend, there is only increasing pressure. If you remain in orbit, there is only radiation and gravitational constraint. The planet gives you no stable foothold. And here is the final layer. Jupiter's gravity well is so deep that it reshapes trajectories far beyond its atmosphere. Its Hill sphere, roughly 53 million kilometers in radius, defines a region where Jupiter dominates gravitationally over the Sun. To escape that sphere requires not only clearing the atmosphere, but achieving sufficient velocity relative to Jupiter to avoid falling back. You cannot coast away casually. You must actively climb out of a gravitational basin carved by 1.9 times 1027 kilograms of mass. And if you descend beyond the point where your remaining propellant cannot generate that climb, the outcome is fixed. Jupiter does not need to crush you instantly. It does not need to burn you away in a flash. It simply removes the last viable trajectory. And once that trajectory is gone, Earth is no longer a coordinate you can reach. It is a memory separated by millions of kilometers and an equation you can no longer satisfy. Jupiter protects Earth by swallowing what comes too close. If you go there and cross the wrong threshold, it will do the same to you. Not dramatically, not suddenly, but inevitably, because physics does not negotiate, and Jupiter has more than enough mass to enforce the terms.